not talk so much about analysis. It will be mainly based on the actual platform that we use to do all the analysis on. So a lot of the learnings from different design steps we went through, some of the mistakes, some of the things that we are proud of, and so on. So for at our company, we have an all-in on AWS, so if you are used to that, you will see a lot of familiar terminology, but I've tried to extract the things that are generalizable, so not provider specific in this case. Anyone else? Oh, you're shy, but talented. Cool. So are you data engineers, or are you data scientists, or are you managers? Okay, so engineers? Yeah, oh, good. Then I think you're in the right place. Are you data scientists? Oh, yeah. Are you business managers deciding, oh, yes, that's okay. Any architects? Oh, good. Okay, so something in for everyone, I guess. Cool. Yeah, so on the topic of what we're actually doing, I've given 2 talks before at this conference previous years, and you actually can find them on YouTube. Let's see what it's, the first one. Yeah, the first talk I did 2 years ago was about anomaly detection and the problem of analyzing on moving data. When things move too fast and changes, and you don't control it. So that's mainly on what now I will talk about the backend platform for that. And last year I actually did a session on anomaly detection and how to put that in production without any limits of asking IT, can I deploy my R code in your production environment? Said no, it's not ISO certified. So okay, people are still coming in. You're most welcome. I have so much to say today, so I will not wait for everyone to sit down. My name is Bresell, and the title is Learnings from 3 Generations Real-Time Big Data Platforms. So, one slide about our company, Telenor Connexion. What we do is that we provide SIM-based global connectivity for machines. There are lots of those operators out in the world, but we are the 2nd biggest out-of-footprint operator in the world. So that means, Telia is big in Sweden, but they only had 2 million. We also have 2 million things in Sweden, but we have 12 million in total, but they are spread across the world. That does not Telia have. Some of our customer brands are Volvo cars, Volvo trucks, buses, Scania, Husqvarna. And the Nissan Leaf cars are connected, lots of smart metering, electricity meters and stuff like that. What more? Home alarms, of course, and so on. We don't own any mobile network on our own. We are borrowing networks wherever we go. So we have roaming agreements and good prices for 400 operators across the world, which means that you can, within one single SIM, you can connect everywhere and have one invoice. And that's sort of what the enterprises and business want when they move into IoT and have connected products. One slide about data. So just to be sure that everyone understands, we are not analyzing the payload data, so the sensor values, the things that the machines actually sends to our customer's backend. What we analyze is connectivity metadata. So it's the control plane, primarily, which means that the things that are happening to establish a data session, or being able to do a voice call, or sending an SMS, handshakes in the networks. So what the SIM is doing, where it's doing it, when, why, and what the error codes, and so on. We have about 500 million events coming in per day. And we also have file-based data coming in batches. That's not real time. It comes in SFTP every hour or something like that, but almost the same amount of events per day. These have two nature. One is coming from the operators, because when our SIMs are doing calls in another operator, they want to get charged for that, okay? They're doing traffic in the network, so they send that operator sends a file. These are the number of calls, and we're going to get paid for that. The second is that we want to get paid from our customers, so we go through the same list of calls, rate them to a price list, and then we send the invoice. Okay. So those we also have in our big data platform. And then, of course, we need some reference data, like how to understand what the transactions actually mean. All the data comes in are like standard data that are interchangeable between different operators. So if a SIM is doing something, we need to add the customer to that SIM in order to understand which customer is driving cost or so on. The same goes for operator. One slide about our architecture, and I will not stay very long on that. Our solution is based on a real-time streaming engine for decoding these binary encoded real-time stream from the control plane. We have a data warehouse based on a columnar principle. It's called Redshift. It's an AWS service. And all our platform, we took a decision back in 2014 or something, that because we didn't have an IT department, we didn't have a development department, nothing. So when we started to build and innovate again, we just went to the cloud and we took the biggest provider in the world. And we're very happy about that. The long-term data goes into something called S3, which is just an extremely scalable storage solution. You put something on there and you have a key for it. And if you put it with a key with a structure, so like year, month, date, you can go back and find specific time slots of data. But all the data will just be randomly there, putting for that date. Okay, so I tried to distill 5 years of experiences down to 20 minutes presentation. And it took me almost 5 years to do that. And this is the way I do it. I just some structure table here. So first row is first generation. What does it say? Well, our architecture was based on a reference architecture for AWS. The streaming engine, where we did all the processing of the incoming data, that was binary. We had to like split ones and zeros, more or less, to decode it. That was done in Kinesis, which has worked extremely well. We haven't changed it or touched it more or less 5 years. It's very, very performant. The data then is fed into a data warehouse, this columnar-based data store. You can run SQL on it, as any database, and it's extremely performant on aggregating stuff. It's designed for read lot and write seldom, and we'll come back to that. The cold data, so like the archive, which we go to seldom, is then on the S3, which is an object storage. Or for the average user, it would look like a big disk surface. Okay. How we analyze most of our data, we use Spotfire. So those that don't know a typical Spotfire, it's the same as Tableau or Power BI, but much more geared towards ad hoc analytics and more fitted. Like if you don't know what you're going to analyze, it's really nice to analyze anything, and you can drag and drop and stuff like that. It's really nice. Yes. So let's look at the first problem we encountered in the first generation. Well, not S3 was not a problem. But at that time, the standard way of doing big data was doing Hadoop clusters. Okay? Have anyone been around for that long? Oh, yeah. What did we think about the Hadoop? Ooh. Basic. Yeah. Basic. The concept was really nice. But we were so proud of this concept because we used a service called Elastic MapReduce. So what the traditional big data company was doing, they were collecting all the old legacy servers, put them into cluster, maybe they bought some cheap hardware from somewhere and then put it together. And they started filled with data. And after a few months, the cluster was full and they had to expand it. Okay, so they went to the purchasing department, which then went to the provider, waiting for them to ship the servers, and then waiting for IT to configure it. So a process that could likely take 3 months or something. That's how you scaled it. We on the other hand had all our data stores in S3. So with Elastic MapReduce, the EMR, you just go into the AWS console and say, give me a cluster of this many nodes, wait 5-10 minutes, and you have the cluster. Then you copy all your data from S3 that is of your interest, that you want to analyze on right now. So take maybe last month of data, move it into the cluster, run your queries in Hive, do your SQL, and then when you're done with the report, you just kill it. And what you pay for is only the node hours. So number of nodes in the cluster times hours you use it. Very neat. Where did this go wrong? It was Hive, because Hive sucks, or we sucked at Hive. I don't know which. But is anyone using Hive anymore? Okay. Maybe you can teach me how to do it. I'll give some sort of answers to it, why we failed. But we did not have good knowledge about how to configure our partition keys. We thought it was like, it's SQL, so let's do that. What we learned from RDS, or like relational database, and then moved it over to Hive, and it did not really fly. We took like weeks to develop a report. And it killed our creativity and innovation capability. So it ended up that we actually used this cluster almost the full month anyhow, so it was not much difference than going by them on our own. But yeah. The one thing that actually worked really nice was to develop native MapReduce applications. And remember, we were very novel to this big data. We never built anything before, so this was our first time. But we came up with this. We had to find, because this first generation was all about operational data, troubleshooting, understanding problems with customers, SIMs, or operators, okay? So when a customer called in and they said, yeah, we had a problem with this SIM, and it started last week. We went to our data warehouse and said, okay, we just keep data there on event level for 48 hours. Okay, so we had to go to our archive. Do we need to spin up a cluster? No. We found, we did a batch job every night, taking all the files that we collected or built the last day, and resorted it not longer by year, date, or year, month, date, hour, by thing, year, month, or something like that. This meant that we duplicated the data. Okay, you think, now you paid twice for the storage. Yeah, but we thought storage was cheap, so that wasn't an issue. So now we can actually go back and say, yeah, just give me all the data for that thing, because we had a partition key on S3, just get it very fast. So that was really nice. What we forgot about is that you don't only pay for storage. This service, you also pay for writing and reading. The API calls towards the platform, okay? And we write and wrote and read a lot, okay? Much more than we ever thought of. So we looked at the bill, yeah, it's big, but not that big. And then after a year or so, we just, what? Now we reduce and remove all data. It doesn't go down. What is this? API calls. Okay. Yeah. So yeah. But we can sort of this, if we talk about cost of the platform, we set the cost of in index of 100 up there, so just have an idea. And we had 3 different data streams. So it was not that big. It was like, it couldn't really be solved with old technology, but the new big data technologies really fit for the problem, but it was not impressive. It was not Google, it was not Facebook or something like that. We did have some random congestions. Redshift is nice, it's very high performant. It is transactional safe. And if you have a database that's transactional safe, normally how it solves it is that if you have a data table with disk blocks in it, every time someone reads from it, it locks for everyone else, so others can't write to the same area, disk, okay? And the same goes for the other way. If someone's writing, you can't read it. So, and we had a real-time stream feeding micro batches into this database in multiple times every second. So we had a lot of tuning and screwing, and not screwing, yeah, but yeah, optimizing to do that filter that. But it's still, after many months, it was still random congestions. And when we came to the root of it, it was actually really buggy SQL clients among the business users that when they dropped connection, did not release the read lock on the table. So the Redshift couldn't clean up the data that was moved over to the archive and so on. It couldn't fill with new data and so on. So yeah, the lessons learned here, well, don't design a solution that race for resources or like where you need read and write to the same computational resource, okay? Try to avoid that as to the extent that you ever can. Okay, so the second generation, you remember the first one was on operational data, troubleshooting and so on. The second generation, we had a new additional scope. We went into the business intelligence domain. We had lots of data, and the only way to analyze which customer was driving costs, which operator was driving margins and so on, was to actually analyze all this data. There was no other else that could do it for us, so we had to use the big data platform for it. But that required us to add 9 more data streams to the platform. And if you look at the old platform, the generation 1, we developed each data stream, 3 of them, as like standalone, individual way of processing and so on. But we thought, now is the time to think about industrialization. Can we find generalized patterns, how we process stuff through the data pipeline and reuse that pattern? So we did. But first I'm going to just visualize how it looks like. This is our data platform. We call it Mr. Machine. I don't have time to discuss that, but we can take a question afterwards. We have our real-time data stream. Today we have 4 different protocols coming in. We have our files coming into through SFTP, and we have reference data. Then we have a lot of applications on there that consumes different sets of data. And of course, everything goes to archive also. So if we go down to one of these, we call it data stream, because it's not real-time data stream when it's in the data warehouse, but it's still like we pass through a lot of different processing steps. It's like a stream in that sense. So what we did, what is we doing in each stream? Well, first of all, we import, receive the data, have to store it somewhere. Then before we do any aggregates or reporting, we need to validate it, because for us, we had to see that we actually did all the mappings of the reference data. Could we map every transaction down to an operator? Could we map every SIM to a customer and so on? So we had to validate. So we had this kind of standardized process looking for that. And then if it failed, we put it in quarantine, and maybe we could fix this by adding new, better reference data the next day, and then rerun it and rotate it. Okay, so this is what we have on event level for 48 hours plus. And then we move it to the archive, so we can search for any time span. But once we have validated, then it's time to refine and combine it with different 2 data tables, merge it, or do aggregates and stuff like that. And we aggregated like SIMs, that's called IMSI, or SIM is the unit we sell, and then we have operators and customers. And then we did it by 5 minutes, hour, day, or months, or something like that. And then we have our applications. And one way, now we had financial data and operational data. So it was a little bit sensitive. Maybe everyone shouldn't see all the data. So we came up with this way of producing a presentation layer inside the data warehouse where we can control user access. This user group can only see this data schema and so on. So it's not rocket science, but it solved our multi-tensity problem and meant we didn't have to have different platforms for different data. We could use one platform for everything. So that's how we solved that. So now the biggest improvement in the second generation was that we could generalize this stream processing. So there comes a few benefits of this. First, now before it took like 3 weeks to add a new data stream. And then we have a stability period of like several months. But now we can add a stream in just a few days, and the stability period was like a week or something. It was much, much faster. The second thing is that if you industrialize and systemize the way you're doing things, the testing framework that we built then could be deployed to all the data streams, okay? So then you can drive quality, integrity of the data, make sure that everything was actually working. So there comes a lot of benefits, not just efficiency. Okay, so 4 times more data, but 40% less cost. And I guess the generalized stream was one part of it, but we could also, we did things more efficiently, removed cost drivers like moving things on S3, forth and back, and so on. So we could also do a 6.5 times improvement overall. That was really nice. One thing that we actually did was to get rid of this EMR Hive solution for doing reporting. Okay, we didn't want that, but we knew what was important, so we did start to aggregate all that inside the data warehouse. And one thing that made this successful, which we failed in the first platform, was that we were very strict on whatever we aggregate, it should always be additive. Okay? So if data comes in late, we can put it to the same dimension and just put new rows, and we can just sum that row, okay, that column. So the problem we did before was that one of our most important metrics are success rate of establishing a data session. Okay, if that goes down, something is not working. For that, you need actually two things: the number of attempts and the number of successes. So rather than compute that on the fly on the aggregation, we just kept the original sums that were additive that we could just keep on filling up for a month, or if late data come in, we could just still put it in the same slice. And on the fly, you could do aggregates on a month, day, 5 minute, whatever, and still compute the relationship. It was just by dividing it on the SQL the select line. So that was really nice. One thing that when we threw away EMR, we had to do something else to find those things in the history that we need to troubleshoot. And if we don't use the archive and we didn't want to use the elastic MapReduce any longer, we had to do something else. But we still use this MapReduce concept and define something very elegantly. We defined a function. In this case, it was AWS Lambdas. We deployed it function as a service. Really nice. I can discuss this later. But then the first function was taking two parameters, thing and date. Okay? Then it invoked a second function saying, give me all the files on S3 for that date. I don't know the name of the files, but I know where they're located. So it listed the files, sent the file names back to the first function there, the main master function. And then that invoked a second function that then took the thing ID and the file name and went through the file and extracted the rows for the thing. And then sent those rows back. And the second function could be completely parallelized because it was not touching the same object. And this scaled out tremendously nice. We could scan any time span. If we had 1 day for 40 files, 800 megabytes each, it doesn't matter if we took 2 days, 1 month, it just scaled out very perfectly. So that was really nice. We were very proud of this. We stole the idea from some others, people at the conference of AWS in Las Vegas every year. And we told AWS that we've done this. Yeah, stay tuned. There will be something announced this year for this. And they launched something called step function that solves this very nicely. OK. So moving into the third generation platform, what we did have a problem with. We thought we solved everything, but we were still developing a super big monolith. Okay? Monoliths are really scary to deploy and upgrade. And when we, even though we had all these fantastic frameworks, it took a lot of time to ensure that we didn't mess up the data. So now in this third generation, we are now introducing microservices. We should have done that before. But we actually was doing it was using microservices, but deploying them as a monolith. What you should do is you take your microservices and deploy them as microservices, so you can just update this one and not everything. Okay? Lesson. Second thing, though, we really love those aggregates we produced in the second generation, but something annoyed us very much, and we're still struggling with this when we use the old platform, which is the second generation, which is still live, but we're fixing it right now. That is that when we aggregate, we have a latency of 5 to 10 minutes for the 5-minute aggregates, and that's what we sort of monitor and take actions on. But as the streamline and the generalized stream processing is scheduled and everything that, we have congestions that are very predictable. So every hour, the 5-minute aggregates came around 25 minutes late. So every time our alarms went off, it was like an hour. It was on the clock. Pretty annoying, and could be handled, and it was not elegant. But what it actually, the bad thing was, it was killing our innovative and like trying out and creativity, because we were like sort of afraid of adding new metrics and aggregates. And that's not the way we're positioning you want to be. Okay, we are in the cloud, we have services, it's super nice. You can actually just go into the console, change the number of nodes from, say, 8 to 16, and you double your capacity. And that's happening within 20 minutes or 10 minutes or something, and without any disturbances. But if you throw money at the problem, more nodes cost more money, then there's a fundamental design problem of the solution, okay? So you should do something else. So what we did was that we sat down again and was thinking, we probably should remove all the aggregations out of the non-write design solution of the Redshift. We shouldn't write that often. So we moved that out, and we have now put this in a Kinesis comes in a family of services. It's something called Kinesis Analytics, where you can do aggregates in real time. So this solves two problems. First, it offloads the workload on the Redshift cluster, our data warehouse, but also gives us real-time aggregates that are stable, and they don't compete for resources. Okay, so that's really nice. And then, what more? Yeah, one thing that we solved was one problem. We did this cascading Lambda. I talked about the functions that we implemented and could get any data for a thing in 20 seconds. We loaded into the warehouse. I didn't tell you about that, but it's really 20 seconds giving anything data from any time point into the warehouse in 20 seconds. That was nice. So the solution we built was finding a needle in the haystack. But what we found out that sometimes we were faced with the problem of finding the toothpicks in the same haystack. So maybe someone asked for operator room information, not thing. And that was how we designed the application. It was only finding the thing. And we can, of course, build the same solution for operators, but it required resources from the development, build this function, deploy it, and so on. So fortunately, there are really nice solutions for this nowadays. AWS has fantastic services for this. It's called Athena and Redshift Spectrum. It's schema on read. So you define your table. This is the structure of my CSV files on S3 in this case. And then you just add your partitions. At this key, I find all the data from this date. This key, I find all the data from that, okay? So then you can go into console or connect your GDBC or something, or in this case, Redshift Spectrum allows you to go into your SQL client and your cluster and actually access the data on S3 through table structures. Send in a query, and it will completely scale out using this design pattern we talked about, the cascading lambdas. And how do you pay for this? You only pay for the number of bytes scanned, no infrastructure whatsoever. That's really elegant. So we designed and introduced this solution beginning of this year just to address a use case we thought was done maybe twice, 3 times a month at most. But it turned out that this capability was used by several users several times each day. So what should we learn from that? Well, if there's only one thing that you should take away from my talk is that whenever you design a big data solution, focus on the capability to analyze data, any data. Do not focus on solving specific use cases, okay? Because if there's something, I reflect on all this and see that, okay, every time we did remove something or changed or dropped it, it was too specific. And every time we did something that was generalized, it just scaled out, not in just compute performance, but also in use cases. We can address so many more new questions from the business. So that's my main takeaway. So with that, that was my, I have some more stuff that will come up, but it's not mind-boggling, so I will skip those. Hopefully we have good discussions now, questions, I'll be around now and also later. So thank you very much.